Okay, today's lesson is over section 6.2. It is titled Differential Equations, Growth and Decay. We are actually going to start with a differential equation, and we are going to separate the variables and solve for y. So, given y prime equals 2x over y, the directions want you to solve for y. The first thing you'll want to do is replace your y prime with dy over dx. You want to get all y's on one side of the equation, all x's on the other side of the equation. So this will be y dy equals 2x dx. Now I know how to solve. I am going to integrate both sides. So the integral of y dy equals the integral of 2x dx. The integral of y is y squared over 2. This will equal x squared plus c. You only need to put a c on the right-hand side of the equation. So if I want to solve that equation for y, I multiply both sides by 2, and then I take the square root of both sides. And that would be the answer solving for y. Now, to talk about the growth and decay part of this section, we want to look at a problem, a word problem. If it is worded, the rate of change of y is proportional to y, let's say that is your quote, then I know the words rate of change of y means dy over dt, because we're with respect to time here. The rate of change of y is the equal sign, proportional to y means that there's a constant of proportionality and it's proportional to y. So I have that equation. Anytime the rate of change of y is proportional to y, that equation automatically means that you could write CE to the KT equals y. CE to the KT equals y. So here's the proof of that. It's a separation of variables. I will divide both sides by y. So I have 1 over y dy equals k dt. I integrate both sides. So natural log of the absolute value of y equals kt plus c. I change that to exponential form. My base is e. So that's e raised to the kt plus c will equal y. Now here's the tricky part. Anytime I've added my exponents together, that means there was like bases that were multiplied together. So if I had this, I have like bases, I would add the exponents. Well, e to the c is just another constant. E is the number raised to the constant c, so we call that big C. And then I have big C e to the kt equals y. Now, there's no need to go through that proof every time if you just want to remember that if dy over dt is proportional to y, you know that y equals C e to the kt. Okay, so when will you have to use this? Let's say your problem states the rate of change of y is proportional proportional to y, when time equals 0, y equals 2. When time equals 2, y equals 4. What is the value of y when time equals 3? Is your problem. So you're given the rate of change of y is proportional to y. So that means dy over dt equals ky. Well, we just learned that that means that y is equal to ce raised to the kt. Anytime you're given the initial time value, that's the same thing as your c. C will be initial value. So that means in this case, I know that y equals 2e to the kt. Now all I have to do is solve for k. But I'm given that when time is 2, y is 4. So I plug in 4 for y and 2 for t, which will give me 2 equals e to the 2k. I have to solve for k. So I take the natural log of both sides. That means I can bring my exponent down. Natural log of e is 1. So k will equal natural log of 2 over 2. So now, no matter what time I am looking for, this case I have to figure out when time is 3, I will use the equation 2e to the natural log of 2 over 2 times t. So again, this case I have to solve it for when time is 3, so I plug in 3. I just type that into my calculator, and I get approximately 5.657. And I wasn't given any units, so I don't need to add that. But if there are units, then you need to make sure that you add that on. I'd like for you to try a couple separation of variable problems. So on page 418, do numbers 1 and 5. And I will see you tomorrow.